Let's take a look at, well, probably the most common irrational numbers, or set of irrational numbers that we look at, that being surds. Now, surd is basically any number that includes a radical symbol. So surds, we always see the square roots, but cube roots are surds. Fourth roots are surds, fifth roots are surds. They're all surds. They just have the radical symbol. But, and here's the key thing, cannot be calculated exactly. So the square root of 16 is not a surd, because you can work that one out. Oh no, that's 4. Some laws. This one's handy for when we want to simplify surds. Root A times root B, we try and break it into two factors, one of those factors being a perfect square. Division, same deal. Doesn't matter the order we do it in. We can find the square root of the top, square root of the bottom, or we can work out the fraction first, then find the square root of it. And of course, squaring and square rooting are inverse operations, so they will cancel each other out. Here's an interesting question. If I had written that as the square root of a squared rather than the square root of a squared, what would the answer be? Absolute value of a. It would actually be the absolute value of a, because you might have the square root of, say, -2 squared, which of course you can work out because -2 squared is 4. But the answer would be 2, not -2, so it's the absolute value. Whereas in this one, it's just a, because now I'm saying square root of a, well, I can't find the square root of a negative number, so a must be positive by definition, so the answer would be a. Square root of 50, okay, two factors. You're looking for the highest perfect square, which in this case is 25. That, of course, is our thought process. We'd probably just write it straight down, 5 root 2. Square root of x cubed, we talked about that earlier, didn't we? Well, theoretically, we could rewrite it as root x squared times root x, square root of x squared. Remember, I just said it should be the absolute value of x root x, but the reason I can get away with that one is why. Notice I haven't gone the absolute value of x root x, even though I just said the square root of x squared is the absolute value of x. Why? Right? Always go back to what the original question was. X cubed couldn't be negative because you can't find the square root of a negative number. So by definition, I know x is a positive number, and I don't need to therefore write absolute value of x root x. Okay, square root of 5 on 4 would be root 5 on 2. I can work out the bottom one, can't work out the top one. Root 20 on 9. Ooh, top one simplifies and we can work out the bottom one. Root 20, that's, I should know that one straight away. 2 root 5, isn't it? Yes. 2 root 5 on 3. Surd arithmetic. That looks awfully familiar. The very first bit of theory we did this year, but there's a different word in there. The very first bit of theory, I said, like terms can be added or subtracted, unlike terms cannot. Why is this exactly the same wording, but I've changed the word terms to surds? What do they have in common? What does algebra and surds have in common? Why can we use the exact same rules for surds that we can for algebra? Yeah. See, a surd is an unknown. We don't know what the square root of 2 is. We just write it as the square root of 2. We don't know what it is. Well, algebra, that's what a pronumeral is. A pronumeral is an unknown. We don't know what the x represents or the y represents. So it's exactly the same thing. It's just instead of using a pronumeral, I might be using a square root of 2 or something like that. So the same rules apply. So if I get something like that, 4 root 3 plus 6 root 2 minus root 3 plus 2 root 2, all right, I don't know what the root 3s are, but I know I got 3 of them. I don't know what the root 2s are, but I know I got 8 of them. And I can't add them together because it's like adding an x and a y. We can't do it. We can't add x and y. So, binomial products, exactly the same. First, outside, inside, last. The difference with surds is sometimes, doesn't happen in this one, sometimes you can simplify the surds down and tidy it up. This one doesn't, of course, because we've just got root 3, root 2, and root 6. Difference of 2 squares. Root 2 squared, inverse operation, so they will cancel. What we got there is what we call conjugate surds. So a conjugate is when you've basically got the same expression, but the sign in the middle has changed. So we get 2 minus 1. Be real careful with that because it's so easy to go 4 minus 1 and we end up with 1. Perfect square. So say we get a squared minus 2ab plus b squared. All the rules are the same. That will do us for theory today.